Hey, welcome to our explainer. We hear a lot about plastic in the oceans or carbon in the atmosphere. But today, we're going to dig into a silent crisis that's happening right under our feet, a chemical imbalance in the very soil that grows our food.
So let's just start with a number to get a sense of the scale here. 830 million hectares. That is the global footprint of this problem. It's an absolutely staggering amount of chemically damaged land, and it's a direct threat to our ability to feed a growing world. And just to put that number into perspective, what we're talking about is an area of land larger than the entire continent of Australia. So what is this invisible threat? Well, that's the big question we're tackling today. And the answer is something called chemical soil degradation. Now, what's really crucial to understand here is that this is, by and large, a human-induced threat. It all stems from mismanagement, things like poor irrigation techniques, and especially the overuse of fertilizers that just throws the delicate chemistry of our soil completely out of whack. And really, that's the bottom line. Our own agricultural practices are the root cause. We're the ones altering the soil's natural chemistry, and the consequences are just quietly piling up season after season. Okay, so to really get a handle on this problem, we need to meet the main culprits. There are three primary ways this chemical damage happens, and each one has its own unique method of harming the land. We've got acidification, salinization, and sodicity. Think of this as our quick field guide to the problem. We've got acidification, which is all about excess hydrogen. Then there's salinization, caused by too many salts. And finally, sodicity, from an overload of sodium. Each one has a distinct cause and, as you can see, a pretty devastating result. We're going to break these down one by one. So first up is acidification. This is basically what happens when the soil becomes too, sour. And it's often driven by a super common farming practice, the constant use of ammonium-based fertilizers, things like urea that farmers all over the world rely on. So how exactly does that work? Well, when farmers put these fertilizers on their fields, soil bacteria get to work in a process called nitrification. As they're converting that ammonium into nitrate, which is what the plants need, they release hydrogen ions as a sort of byproduct. And over time, that buildup of hydrogen causes the soil's pH to just plummet. Next up, we have salinization. And this is pretty much exactly what it sounds like. The soil is just becoming way too salty. You see this a lot in arid regions where the irrigation water itself might contain salts. And when evaporation is high, the water disappears, but it leaves those salts behind, building up to toxic levels right where the plant's roots are. Now, it's really easy to mix up salinization with sodicity, but they are very, very different beasts. Sodicity is specifically about having way too many sodium ions. These ions act like little bullies. They literally kick essential minerals like calcium right off the soil particles. And this doesn't just mess with the chemistry, it has a catastrophic effect on the soil's actual physical structure. And that brings us to the consequences, because these chemical imbalances, they don't just stay in the soil. They create this damaging ripple effect that travels all the way from the microscopic world of soil particles right up to the food that ends up on our plates. So with acidic soils, once the pH drops below 5.5, it's like a cage is unlocked, releasing toxic aluminum into the soil. This soluble aluminum then directly attacks plant roots, stunting their growth. And as if that's not bad enough, essential nutrients like phosphorus get locked up, making them totally unavailable to the plant. Saline soils create this really bizarre and deadly situation known as a physiological drought. Basically, the salt concentration outside the plant's roots becomes so high that osmosis prevents water from even entering the root. So the plant is quite literally dying of thirst, even when it's sitting in damp soil. And remember salinity? That excess sodium causes the tiny clay particles to disperse and break apart. It effectively destroys the soil's physical skeleton. The whole structure just collapses, creating this dense, impermeable layer that water can't get through and roots can't even begin to grow through. It's like turning good soil into a brick. And here's where you can really see that ripple effect in action. It all starts with that degraded soil. That leads to nutrient-deficient crops. These crops then become lower quality feed for livestock, which in turn reduces animal health and things like milk yields. And ultimately, the food that makes it to our tables has a lower nutritional value. It's a direct cascade from the ground up. So we've seen the problems and we know their impacts. The question is, how do we start to fight back? Well, like with any illness, the very first step in recovery is getting an accurate diagnosis. We have to learn how to read the chemical clues our sick soil is giving us. And these are the key vital signs scientists look for. They measure pH to check for acidity. They use a measurement called electrical conductivity, or EC, to figure out the total salt content for salinity. And they calculate something called the exchangeable sodium percentage, or ESP, to identify sodicity. These numbers tell them exactly what kind of problem they're dealing with. And today, that diagnosis process is getting a major high-tech upgrade. It's not just about walking fields and taking samples anymore. Scientists are now using remote sensing from satellites and sophisticated GIS mapping to monitor these problems on a massive scale, correlating what they see from space with the actual health of the soil on the ground. Okay, so we've identified the patient, we've diagnosed the illness. Now let's get to the hopeful part, the cure. The good news is we have scientifically proven methods to start healing the land. And what's great is that the treatments are incredibly specific. If you have acidic soil, you add lime to neutralize that excess acid. For saline soil, you need lots of good quality water to leach or flush the salts down below the root zone. And for sodic soil, it's a two-step process. First, you apply gypsum to knock the sodium off, and then you leach it away. But the absolute best recovery plans stand on two pillars. On one side, you have those targeted chemical fixes we just talked about, but on the other, you have what's called biological facilitation, basically using nature's own tools like hardy salt-tolerant plants, compost, and cover crops to help speed up that healing process and rebuild soil structure. And this all comes together in a clear, staged recovery plan. First, you test and diagnose. Then you fix any drainage issues. You apply the right chemical amendment, and then you bring in those living rehabilitators, the tough plants that can thrive in these conditions. And finally, you focus on building long-term health by adding organic matter. It's a patient, methodical process. And that really brings us to this powerful final thought from the source material. It reframes this entire challenge. It's not about finding a single quick fix. It's about shifting our entire mindset to one of continuous stewardship and regeneration for the land that sustains all of us. Which leaves us with this final and I think most important question. Knowing what we know about the causes, the effects, and the cures, how do we move beyond just fixing problems after they appear and start building a food system where regeneration is the foundation? Something to think about. Thanks for tuning in.